Hello, I'm going to talk today about the portal frame method. This is one of the approximate analysis of rectangular building frames, as we said before and as we mentioned. Today we're going to talk about this special portal frame method. Let's go and have a look on this, okay? Again, we are under the subtitle called Analysis for Lateral Loads. We are under this main subtitle, and then there is another subtitle called Portal Frame Method. If you remember last time we were talking about the vertical loads. This time we're going to talk about the Portal Frame Method. Okay, now let's go through this. First of all, for our Portal Frame Method, we need to have some assumptions to be taken and considered in order to make our appropriate analysis, or at least to make the approximate analysis for the building that we are investigating. First of all, this method is considered to be appropriate for approximate analysis of relatively low buildings. As we said, it is for low buildings. Okay, it is not recommended for high-rise buildings. Okay, multi-story. This is better for the low-rise building. This is number one. Number two, we are going to look to the deflected shape of the structure. As you can see here, we found that we have for each frame there is inflection points at the mid-span of the columns and the girders. So this is going to add for us what we call it what? Exactly. It is going to add for us equation of condition based on an internal hinge that is going to be introduced at the middle of each point, or at the middle of each column and girder. Okay, so this is what we want to highlight here. If we have a lateral load, okay, that is being applied on a frame, then the inflection point is going to take place at the mid-span of the columns and the girder, and based on this we are going to introduce internal hinges at the mid-span of the columns and the girder, and we are going to use a equation of condition at each internal hinge introduced. So we changed the portal frame to a simplified determinate frame. This was indeterminate frame. Here it is going to be determinate frame because we introduced a kind of internal hinge here, okay, internal hinge at each column and girder for each loop. Okay, so this means that we are going to find the internal loads based on the new equations of conditions that we have introduced. Okay, now let's go to the next one and look deeper how we are going to see this. Well, if you go back here, we have here, this is point E, this is point F, this is point G. So this is point E, this is point G, and here this is point F. Okay, so if you want to solve the portal frame, look here, we are going to start with, for example, because there is an internal hinge here introduced, so we're going to start with summation of moment at this point, which is point G, and we're going to take the counterclockwise to be positive. Then moment here should be 0. This means that all the forces that is passing through this G is not going to make any moments. Based on this, we are going to have only one component, which is the internal force in the member CA, which is, we're going to call it like EY, the vertical member or the vertical reaction here, okay, times this distance, which is the distance of the bay, okay, which is going to be L, for example. And this is what we are going to do here. So EY times L, EY, this is EY, okay, times L. L is the distance. Let's put it here. This is the distance, and you can, if we go back, this is L, which is the distance, okay? Okay, so minus P times H over 2, P times h over 2. This distance, it is h over 2. So equal to 0. We're going to find that gx does not, hasn't been included, gy and ex. Why? Because they are concurrently, or they are passing through the point where that we are taking the moment around. So from here you are going to find that it is only one equation in one unknown, which is ey. Then we can obtain ey, which equals to ph over 2l. Okay, and it's heading down. Okay, so we know this. Similarly, we are going to take the summation of the forces in the y direction. Okay, is going to be positive upward, equal to 0. Then we are going to get, yes, exactly, this gy, right? This gy can be obtained easily from the summation of y. It is going to equal ph over 2l heading above. Okay, and then if you go to the point F here, we are going to take the moment around this F for the part EF, this part, all of this part, okay? What will happen here? We're going to take counterclockwise to be positive. So we're going to find that pH over 2L, which is EY, already we know this. This is EY, and already we obtained it before here, okay? Times L over 2, which is exactly the moment arm, which is L over 2, this distance from here to here, L over 2. Then we minus EX times H over 2. This is EX, already EX times H over 2, which is the half of the height of the frame. From here we can obtain EX because it is the only unknown. Now we know EX to be P over 2. As you can see here, if you look to the equilibrium equation of the part ECFDG, you're going to find that Gx must equal to P over T, because P over 2, because we have P here and we have P over 2 opposite to it, so this must be P over 2. Okay, so now this is the benefit of introducing the internal hinge. We get benefit from these. We have the summation of moment of G, summation of moment at point G, summation of forces after that, summation of moment at point F, and then the summation of forces, the horizontal forces. We could obtain all the values that, or all the unknowns that we are seeking for. EY, EX, they are the reactions at point E, the horizontal and the vertical. And then GY and GX, they are the two horizontal, or the two unknowns at point G, GX and GY. Then now we know the four unknowns at point E and G. Okay? If we know them, then we are going to reverse them to the bottom half of the bay. So here it is going to be PH over L, and here it is going to be P over 2. This is heading to the right, opposite to GX. This one, or this component, or this reaction heading down, opposite to GY, which is heading up. In a similar fashion, we have here PH over 2L heading up, P over 2 going to the right. Then we have here a cantilever, which is having a fixed support at the bottom, right? Simply from summation of X, this is P over 2, then the horizontal reaction at A, which is AX, should equal to P over 2. Okay? And we have PH over 2L heading up. We must have AY equals to PH over 2L heading down. Then we know this. We know this reaction now. And at the end, we want to know MA. If you look here, P over 2 is going to make the moment. However, PH over L will not do anything. Then the moment here, in order to maintain the equilibrium of EA, should equal, which is MA in this case. We take the moment at A, then it should equal minus P over 2 times h over 2, which is the component at E, horizontal component at E, plus MA. From here we can get MA equals to pH over 4. pH over 4. Similarly, we can apply the same procedure for the part GB. Okay? Then after that, we already know now everything. We know all the reactions, horizontal reactions, vertical reaction, and moment at point A and also at point B. Okay? So after introducing our internal hinges at E, F, G, this solved everything for us. Using this procedure, you're going to find that we have solved the frame easily. We could obtain the reactions and the internal forces as well. Then it is very easy for us to draw the bending moment diagram if we are seeking for the bending moment diagram. Okay, so it is easy for you. I think that all of you know this from structure analysis 1. You can draw the bending moment diagram. Already you have the moment at B, the moment at A, which is pH over 4, pH over 4 because of symmetry. If you look, you are going to find that we have a symmetry axis, so you can simply just solve half of it, and the second half is going to be the same based on symmetry. We have pH over 4 here, and at this point, which is point E, there is an internal hinge, or there is point of inflection, so there is 0 here, 0, and then at the top it is pH over 4. Already we have obtained this. Okay, pH over 4 from P over 2 times the distance, this distance. And if you go back, already we have this value. Okay, so pH over 2, which is P over 2 times this, which is H over 2. This is pH over 4, and it equals to P over 2 times H over 2. Okay, and take care of the sign, because outside of the frame is going to be like, take it, for example, inside is going to be positive, outside is going to be negative. It is based on your sign convention. Okay, similarly here it is going to be pH over 4 from the equilibrium of point C. Okay, and then here we have internal hinge, which is 0. And the rest of this would be based on symmetry. So you are going to copy it exactly. Okay, so this is very easy and super simple way for solving our structure, based on the introduction of internal hinge at point E, point F, at point G. Okay, now let's go to some assumptions for multi-stories, and let's see how we can solve and how we can go in a systematic procedure. So the assumptions here are that an inflection point is located at the middle of each member of the frame. So as you can see here, we have, these are the inflection points, as we said. These are the inflection points of the columns. And we have inflection points as well for, exactly, for the girders, at the middle of the girders. Okay, so these are the inflection points. And number 2, on each story of the frame, interior columns carry twice as such shear as exterior columns. This is very important assumption that we are going to take care of. Let's have this. This means that whenever that we have lateral loads applied, like P1 and P2, as you can see here, the exterior columns are going to take, for example, like the shear, 1 shear, and the interior columns are going to take 2, okay, 2 shares of the shear. Okay, we are putting it like this. Interior columns, double of exterior columns. Okay, clear. Okay, now let's go to a systematic procedure for the solution. Okay, and this systematic procedure, I want you to memorize it well, because it would help you a lot when you are proceeding in the analysis. Okay, so here, number one is draw a sketch of the simplified frame, putting the dimensions in it. And number two, determine column shears. Remember that very well. Column shears in the beginning. After that, you are going to make our main assumption, which is the shear in the interior column is double or twice the exterior columns. Okay, and number four, draw free body diagram of all members and joints and external loads and column shears. Remember well these hints. Okay, so we're going to draw free body diagram, putting the external force and the column shears that you already obtained in the previous step. Then determine column moments. Okay, and remember that small hint here, and I'm going to recall this hint later. Column moments are equal and have the same sign at the end. Look here, this is column end moment, MC. This is the top end. They are having the same counterclockwise orientation, and they are having the same magnitude. Okay, remember that well during the analysis. Okay, and this MC is going to equal to SC, which is the shear of the moment, the shear of the column, times H over 2, which is exactly half of the column height. So they are equal in magnitude and in sign as well. After that, step number 6, determine the girder axial forces. This is the girder now, axial forces, moments, and shears, and apply the equilibrium equations. Start from the top to the bottom of the frame and from the left to the right. Remember that very well, and you are going to see it during our analysis and our example. For the beam, as you can see, whenever we have the beam, we are introducing an internal hinge at the middle, right? Then we're going to have the moments that we have obtained already from the columns are going to be reversed here on the beams. So these ones already, they are known. And taking the moment here, the moment here should be 0, then we can obtain SG. So SG is going to equal mg over half of the girder length. Okay, from here we can obtain SG, and SG, as you can see, they are what? Exactly, they are opposite to one another. So this is in this direction and the other one in this direction, because they should be equal in magnitude but different in sign. So this is SG left, this is SG right. Okay, and number 7, determine column axial force. The last thing is column axial force. Remember that very well, starting at the top and top story. Okay, starting from the top story, starting at the top story. Okay, use the 3 equilibrium equations of the entire frame to check the calculation. This is the final check for you. This is the final check for you. Okay, clear? Okay, now let's have an example. You're going to see that this example really going to help you a lot in understanding the systematic procedure. We have a frame which is 10 meter span and 8 meter height. There is a lateral load applied at point D, 60 kilonewton, and we want to solve this example based on our systematic procedure. So first of all, we are going to use our simplified frame by introducing the internal hinge at the middle of the columns and the girders. Okay, so this is number 1. Okay, and then we're going to take a section just above the fixed support at the bottom, which is going to be, as you see in this figure, and as we said, shears are going to be calculated easily. Here this is S, this is 2S, here S. If we say this is 60 kilonewton, then without thinking, this one should be 15, this one should be 15, and this one should be exactly 30. So here we have 15, 30, 15. This would give us 60 applied here. So we obtained the shears at the columns or in the columns. We obtained the shears in the columns. Okay. Now let's go to the detailed one. Do not fear from this. You are going to find that it's very easy when you go into the details. Let's go let's have the highlighter here, and I think that it would be better for us. First of all, remember that the first member or the first value that we know is the shear, which is the shear of the column. So this one, 15, as I said. And from the equilibrium equation for the horizontal forces, the top column shear should be 15 as well. Okay, so we know this. We know the shear and we know the shear. And we should know the moment here, which is 60, because this, from the equilibrium at this point, this is 15. So let me use another one. On the highlighter, it's the pen here. So this is 15, we know it. This must be known because this is 60 is going to equal 15 times 4 using the equilibrium or equation of condition at this internal hinge. So we know the moment, we know the shear here. For this column, this top shear should be 15, similar to this, the bottom. And the moment should be 60. Why? As we said, do you remember the hint? Let's go back to the hint that I said here. Yes, column moments are equal and have the same sign. So without thinking, this should be 60 and we know it. Okay, so now we know this 60. So we know everything now for the column, the shear, the moment, the shear here and the moment, but we do not know the axial force. Axial force are not going to be known now. It is going to be known later. Okay, now let's go to the second point, which is going to the joint D. This 15 is going to be exactly reversed here. So we know this 15. And this moment is going to be reversed here. So we know the 60 now, right? We have 15 here. We have 60 here. From the horizontal force equilibrium, the QDE should be 45, which is 60 minus 15, so it is 45. From the moment here, which is 60, the moment at the end of this joint or the end of the girder DE should be 60 as well, from equilibrium of moment at this point, at point D. So this is 60, which is, as you can see, it is what? Counterclockwise. And this one is what? Clockwise. So they are same in magnitude, different in orientation to maintain equilibrium. Okay. Okay, so we are okay now. Now we know the moment, and we know we know the moment here, and we know this axial force, right? This moment is going to be reversed at the shear. So we are going to put the 60 here. Okay, we're going to put 60 here, and they are going to be clockwise. Okay, and this QD is going to be reversed here, and it is going to be heading to the right, so we know it. Knowing this moment, which is 60, at point D, taking the moment at the internal hinge, we can obtain this shear. This shear SDE equals to 60 over 5. 60 over 5 would give us 12. And then from the equilibrium of the girder DE, we can obtain SED, which is the shear at the right of girder DE. It is going to be the same as this, but different direction. Taking the moment here at point at the middle of the girder DE, we can obtain MED, which is going to be 60, right? Okay. Knowing this QDE, which is the shear, which is the axial force in this member, in the girder, we can obtain this axial force at point E. Okay. As you can see here, we know everything now about the girder, right? We know the axial force, we know the shear, we know the moment at point E. Similar at point D, we know the shear, axial force, and the moment. Okay? If you go to this joint, which is the joint that we were talking about, everything is known except for there's something that is missed here. Yes, exactly. We obtained this 12, so we need to reverse it here. Exactly. It should be reversed. This is heading to the bottom. This should be heading to the top. From this 12, we are going to exactly reverse it here at the bottom of the joint D. And from this QDA, we are going to reverse it here simply, right? And then we are going to reverse it at the bottom of the column, which is QAD 12. Okay, understand it? So this is the axial force of the column. Actually, this is only for illustration. We should not go to the axial force of the column at this stage. This is only for presentation now. But actually, when we are going into a huge problem, axial forces of the column should not be in this case. Axial forces of the column should be in this stage. It should be at the end of solving all the girders and all joints. Then we can go through the axial force. Let's continue with this one and put drawing the whole diagram as in the steps. Remember, in the steps we said that draw all the beams or the girders, columns, and the joints as well. So now we, as you can see, we draw everything here. We draw the columns, and we draw the girders and the joints in between the girders and columns, as you can see. Okay, what we have here, already we know this part now, so we know that we have obtained this 15. Let's have the, okay, let's with the green color now, 15 and 15, 60 and 60, which is the moment already. So this is here 15 and 60, it is known for us. And this 60, we already obtained it. And we mentioned about the 45, okay, because we have this 15, so it is 15, this is 60, so we know 45, we know this, and this shear. So now we are going to put this with the opposite sign, which is the axial force here. So we know the 45 here with the opposite direction. This is 12, then this one is going to be known from the opposite direction. This is 60, then we are going to use this, know this, which is 60 from the opposite direction. This is counterclockwise. This one is, sorry, this is clockwise, this is counterclockwise. This is clockwise, this one is counterclockwise. Okay. In a similar fashion, we said before, this is the column. We should, as we said, we should put all column shear force in the beginning. And in the first step, I put this to be 30 and 50 from the very first step, right? Okay. If we know this is to be 30 and this is to be 15, okay, this means that taking the moment here, we can obtain the value of the moment at B, which is 120, right? And if this is 120 counterclockwise, this should be 120 counterclockwise. If this is 30, then this is 30 in the opposite direction. Similar, this is here 15, this should be 15 in the opposite direction. We know this, we know this. Here, taking the moment at the internal hinge, then the moment at C is going to be 60, which equals to 15 times this, which is 15 times 4. If this is 60, then the moment here is going to be known, which is 60. Okay, now we know the shear and the moment at the column ends for all the columns. Then let's reverse it on the joints. We know 60 here, then it will be reversed here. This is 15, then 15 will be known here. Okay, at this joint, from the equilibrium of horizontal forces, this should be 15. And from the equilibrium of moment, this is 60, then we have moment should be here, then this one is 60. Okay. Okay. And we have, okay. So now this is 60, which is the moment. This 60 is going to be reversed here. This was counterclockwise, this is clockwise. From this 60, we can take the moment here, 60 over this distance, which is 4. It would give us the shear here, which is 12. Okay, and after that, so we know the shear here and we know the moment. Okay. Okay. Now, for the other part of this member, we are going to reverse this 12. It is going to be here with opposite direction, and this 60 is going to be here with the same direction. So we know this now. We know the shear and we know the moment at the ends of the girder. Okay. This 12 is going to be reversed here. This is 12. And this 60 is going to be reversed here, which is this 60. We know this and we know this. Okay? Okay. Remember that the axial forces are known from here. So let's have another color. This is 15. So this one, supposedly to be known, 15. And this would be reversed here, which is 15. And this would be reversed here, which is 15. Okay, so we know everything now for this joint, which is joint E. But we didn't get yet this 30. From where we can obtain this 30? Exactly. This 30 is 45 minus 15. Where is 45? This one. We know it. Already we have obtained it with the green check here. And this is 15 here. So we have this is to be 30. Okay? That's right, because here this is 30. So we are right. We're checking now. Actually, it should not. We should put this 30 here, and we are going to like get this check with the 15 or other figure, but it is okay for us. Now let's have, this is the moment 60 here, moment 60 here. Both of them are counterclockwise, so we have to have moment here, which is 120, and it is counter, and it is clockwise. Actually, this 120, it is similar exactly to what we have obtained from the column. This is okay. Okay, this is a check for yourself. Now let's go to the next part, which is the axial columns. Okay, let's use another color here. Which color that we didn't use? I guess this blue, we can use it. So first of all, start with this left part, the left part. Looking here, what this is the shear of the girder, right? The shear of the girder is 12. Then we can reverse it here to this joint, which is 12. And from the summation of y equal to 0, we are going to have this 12 at the bottom part of point D. And this 12 is going to be reversed here, which is 12. And then this 12 is going to be reversed here because of the equilibrium of the vertical forces for the column, okay, for the column AD. Now this is 12. The axial force here is 12, as you can see. In a similar fashion, look to the shears coming from this girder and the shear coming from this girder. It is 12 here and it is 12 here, right? This is going up, sorry, this is going down and this is going up. This means that at this point, there is no forces in the vertical direction. This means that we have no forces in the middle column. This means there is no axial force in this column. No axial force. Okay. Now let's go to the right column. Look to the 12 here. Okay. this 12 is going to be reversed on the joint, which is 12 here, and this 12 is going to be reversed at the bottom of the joint, which is 12 here, from the summation of y equal to 0, and then this would be reversed here, 12, and then this would be reversed here, which is 12. This means that the axial column in this, the axial force in this column is 12, okay, based on this. Okay, I think that you need to repeat the same procedure that we have done here. Really, it seems to be a little bit difficult, but actually it is not difficult. I have solved everything starting with the procedure that I have, the first step in the procedure, which is determining the shear and moments of the column for all the columns that we have. Okay, let's have the highlighter better. So starting, sorry, not the laser pointer better. So we started with the columns. So we started with the shear, which is 15 from the very first beginning. We said that the shear at the exterior columns is carrying half of the interior columns. So interior columns is 30. Here it is 15. Here it is 15. Then for each column we proceeded. We said that this is 15 here. From the equilibrium of the horizontal forces, the shear at the top of the column should be 15. And from taking the moment at this point of the internal hinge, we can say that 15 times 4 would equal 60. This means that we need to have 60 kilonewton meter, or 60 moment with magnitude of 60 at point A. Similarly, from the hint that we said, this 60 is going to be with the same sense and magnitude at the top of the column. Now we know the shears, we know the column, the end moments of the columns. This shear and this moment would be reversed on the joint here. Taking the equilibriums here, different equilibrium for moment and horizontal force and axial force, we can obtain the 45 here, which is the horizontal force here and the moment. We should reverse it on the beam or the girder, and then we can proceed to take or to get the moment and the shear of the other point of the girder, and then reverse it on the joint here. So then the forces coming from the right girder and the forces coming from the left girder are going to be reversed on the joint, and then the shear and the moment coming from the bottom column is going to be reversed on the joint, and you are going to check this to be under equilibrium. Similarly, we are going to proceed with this joint and with this column. Okay. At the end, we said that at the end, the shears of the girders are going to be reversed on the joints, and they would be the axial forces in the columns. So the last step is the axial force in the columns. Okay, I wish that you can repeat this again, and you're going to find it super easy after doing it 1 or 2 times. Okay, and then the last step for us is the checking. So we are going to check here that everything is okay. First of all, we're going to check with the summation of f of x equal to 0. And actually this is from the very first beginning, if you remember that here we have 15, 30, and 15 already we have assumed that, and this is 60, so we are okay. This check is fulfilled. Summation of f of y equal to 0. We have here 12 heading down, and we have here 12 heading up, and there is no axial force at point or at column BF, so it is fulfilled. Summation of f of y, or vertical forces, equal 0 is fulfilled. The last one is the summation of moment at any point should be 0. So we're going to choose MC, which is at point C. If you take the moment here, we're going to find that if we take that counterclockwise to be positive, then at point C, we're going to find that the 60 is making negative moment. 60 times this distance, which is 8, minus 60 times 8 here. And then we are having 12 times 20, which is 2 spans, plus 60, which is the moment here, plus 120, plus another 60. If you check this, you're going to find it 0. This means that our assumption and our procedure was right. This is the final step for you to be 100% sure that what you have done is right. Okay? Let's go to a more complicated example, and we are going with the same procedure, with the same steps of the procedure, and we are going to find that it's very simple for you. Okay, now we're going to have two-story. Okay, it's a two-story frame building. It is similar fashion. We have 10 kilo when 10 caps here at point G, 20 caps at point D. The spans are not the same. Here's 30, here's 20. And the distance or the height of the floors, they are not the same. Here's 16, here's 12. Okay, so we are going to take, as usual, first of all, we are going to take this section cut, which is section, we call it section AA. Let me use the highlighter or the pen here. So we are having, here is A. Let me use another color. So this is AA. We're going to check this. After finishing this section, getting the shears and moments and axial forces of the girders and columns, then we are going to reverse everything on the second part, okay? And we are going to take the section BB for the calculation, okay? We are going to introduce our internal hinge at the middle. Remember here, this is 15, this is 15, here is 10 and 10, and the middle here is going to be 6 feet for the top story and 8 feet for the first story. Okay. Now let's go with the section. Remember, we are talking about section AA. Go back again. This is AA. Then here it is pretty simple and similar to what we have done before. Okay. We have here, first of all, the shears of the columns are going to be distributed based on our understanding. As we said here, this is 10. So definitely without thinking, this is going to be 2.5. This is going to be 5. This is going to be 2.5. And then for the section BB, the shears are going to be the accumulation of 10 and 20. So here we have both of them. They are 30. This means that we need to look to this. This is going to be like 7.5, this is 15, 7.5, 7.5, and this is going to be 15. Okay, so this is from the very first beginning. This is the most important step, which is the shears of the columns. If you could put it right, then it is a right start for your procedure. Okay, now let's go with the top part. Now we're talking about this part, this part, okay, which is DG until H, for example, with 10 kips only at point G. Here, 10 kips. Take care of the points here. This is the 10, okay, and this is 2.5. Already they are known for us. So this is known, this is known. Okay. 2.5 here from the equilibrium of the column. This is going to be 2.5. This is heading to the left, this is heading to the right, so we know this. Taking moment here, then we're going to get mdg, which is 15. 2.5 times 6, it is giving 2.5. Moment 15 here, this moment is known, it is going to be 15, and in the same sense. So we now know the shear and the moment of this column. Then reverse this 2.5, it is going to be here. And the moment, which is 15, it is going to be here. Taking the moment at this point, at point G, for this connection, this is 15, this must be 15. This is 2.5, here we have 10, then QGH is going to be 7.5. Put this 7.5 here and reverse it, so we know this. This 15 is going to be reversed here. Then we know this, okay. Then taking the moment for the girder, as we know. Now we are going into the girder, taking the moment here, and knowing this moment, which is 15, then we can get the shear, SGH, okay. So we know the shear here. We know the moment, we know the shear, and we know we know the moment, we know the axial force, and we know the shear. Looking to the right of this girder, we're going to have moment here 15, because this is 15. They are like in the same sense, in the same magnitude. Similarly, this one is going to be different, or the reverse of SGH from the equilibrium of Y, and this definitely 7.5, similar to the axial force from the left. That easy. We can solve one loop of the complicated frame. Let's go to this really kind of little bit complicated, but really whenever that you think about it, you are not going to find it's complicated at all. Okay, I'm going to check, just making like this for whatever that we know, and then you are going to understand it's really systematic. Okay, starting with the shears, what we know first, I'm going to check it. First things first, 2.5 we know it, right? And here 5, 2.5 I know it, 7.5 as we suggested, 15, 7.5. Okay, now we are going to start from the top and the left. Okay, I think that this part already we have done it. Okay, so I'm not going to do it again. We know 15, 2.5, 15, 2.5, 15. This is 1, this is 7.5, 15, 7.5, 15, and this is 1. And here we reverse it, 15, 1, and 7.5. Okay, so everything here is known for us except the axial force of the column. Now, let's go. This is 7.5, put it here, 7.5. This is 15, put here 15. Okay, I mean, this is 15, then this is 15. This is 1, reverse it, 1. Okay. Okay. This is for this column, for this girder. Now we know this 5. Put first everything for the column to be clear. So this is 5 here. We are going to have a 5, another 5. This is 5. Shear, we have 5 shear. Moment here is going to be 30. 30 means that 5 times, yes, 5 times the 6, which is the half of the height. And here is the 30. Similar here for the column. This is 2.5. This is 2.5. Here is going to be 15, which equals to 6 times 2.5. Here this is 15. Then reverse everything on the joints. 2.5 here, 2.5 here, 15 here, then 15 here, the same. 5 here, 5 here, 30 here, 30 here. Okay, now everything is known now for regarding the top columns. After that, we are going to put, look to this joint here. So we have like moment here, which is 15. So we need to know that this is the moment 15 here for equilibrium of moments. We have 2.5 here. Then there must be 2.5 here, right? And in the opposite direction, as you can see it. Okay. And then this 2.5 is going to be reversed here on the girder, which is the axial force of the girder. Okay. Now, for, yes, okay. Now, this moment, which is 15, is going to be reversed on the girder. This is the 15 here. And this 1.5 on the joint, going to be obtained from the girder. Take care of this because this is a little bit tricky. Actually, we reversed the moment here, taking the moment at the internal hinge, then 15 over this distance. It would give us, this distance is 10, so 15 over 10, it gives us 1.5, which is the shear of the girder. This shear of the girder is going to be reversed on the joint, which is 1.5. Okay, take care of this. Okay, and then here for the girder, let's continue with the same color here. For the girder, we have, this is 1.5. Definitely this would be 1.5 unknown for us from the summation of the vertical force. 15 moment here, 15 moment here with the same sense. Okay, moments are the same sense for the girders, but shears, they are different sense, different direction. Okay, we know this 2.5, then we know this 2.5. Okay, and then we are going to reverse everything here. This 1.5 is going to be reversed here. This is 15, then we have 15 here known, This 2.5 here, we know 2.5 here. Now this joint and joint H, everything is known for us. Everything is known for us. Let me zoom. I do not know how to zoom actually. It seems it's not working. But anyway, this is H here. Then based on this, we know everything. We know everything here. The important thing here is this is 1.5 and here this is 1.5. Okay, there is 1.5 here. Sorry, this is 1.5 and this is 1. So this vertical load from summation of y, it equals to 1.5 minus 1. So we have 0.5 here and another 0.5, which is going to help us in the axial force. Similarly, these are the values for, now we know everything for the girders and for the columns, for the top story. Then everything is going to be known for us for the bottom story. You can do the same. Similarly, the same. Start from here. We have 7.5 and 60. This one 7.5 and this would be 60 from the equilibrium of moment and horizontal forces. Reverse that here and here. And from the top here, from this one, 2.5, it is going to be 2.5. 15 here, 15 here. And then remember that we have external force here. Take care of this, 20. Okay, so here at this point, point D, we are going to take the summation of x. You're going to find that we have 2.5 here, and we have 7.5 from the bottom. Then this should be 15, which is the axial force of the girder. Reverse it here. So we know this and we know this one. Summation of y at point D would give us, okay, so this is at point D. Now let's go to the girder here. This girder, we know the moment, yes, summation of moment at D. We know 60 here. We have 15 here. So this must be, this is 60 and this is 17, so 15. So this means that this one is 75, which is the moment at this point. This 75 is going to be reversed here. So this is another 75, okay? And from this 75, taking the moment here, we can obtain the shear at the girder. This is the shear, and this shear is going to be reversed here. And this moment is going to be the same sign here, okay? That's it. And then similarly, you can get the same procedure, go from also here. This is known for us, 120, 15, and this is 120. You are going to reverse this here, this 15 and 120. Similarly, you are going to reverse both here, 15 and 75. And from here, you can reverse this. So you have this 30 and 5. Similarly, you can go with the frame. You have 7.5, 60 here, 7.5 and 60 here, as you know from the equilibrium. And then you can proceed to this 70.5, this is 60. And from the top here, this is 15 and 2.5, as we have said. Taking the equilibrium of moment, then we can get 70.5 here. And then, sorry, this is not this one. Let me erase it. Sorry, it's not this one. We should take the summation of moment here. So we have 60 and we have 15. So this should be 75 moment. The 75 moment is going to be reversed here. From this 75, we take the moment at the internal hinge. Then we can get the shear. And from this shear, reverse it here. Then this is 7.5. This 7.5 is going to be used for the axial force of this column, okay? But take care, 7.5 from this girder, and there is, yes, 1.5 from the top. It comes from the top. This is 1.5, 1.5, reversed here, reversed here, reversed here, and then this is 1.5 plus 7.5. They are going to give us 9, okay? I think that it's a little bit, let me use this laser point. I think now we have solved, as you can see here, we have solved everything regarding the shears, moments, and axial force of all girders, and shear and moments of the columns. The last thing is what? Exactly. It is going to be the axial columns, axial forces in columns. And this is actually going to be, let me use another one, which is this one. Simply, I'm going to give you an example. This is here, already we have obtained it, which is 1. It is going to be reversed here, which is 1. And it's going to be reversed here, which is 1. Then this is the axial column. It's going to be 1. And then reversed here, 1. And then it is going to be, take care, it will not be reversed directly because we have 5 coming from the shear of this girder. So we have 5 and 1. They are going to give us 6. The 6 reversed here, and then the bottom is going to be 6. In a similar fashion, you can obtain this 3. Okay, from the starting from the girder 1, this is 1 here, this is 1.5. We have this is 0.5. This is reversed, 0.5 reversed, and then this 0.5. This 0.5. We have 7.5 here, and we have 5 here. 0.5, 5, and 7.5. Summation of x, summation of y would give us 3. Hitting bottom, reverse it here, and then end with 3. Similar fashion here, we're going to find 1.5, 1.5, and then 1.5, and then you're going to find here, it's a little bit crowdy here, so we're going to find 9 here because it comes from 1.5 here, and you have 7.5 here. So this would be the 9. Okay, so 1.5 plus 7.5 equals to be 9, which is here, and this 9 is going to be in here. Okay, can stop the video at any point and you can check what we have done. It's really, I know it's a little bit messy, but you can go from the very first beginning and you can check what I've done. Okay, now we are going to check, let's use the laser pointer. Now we are going to check here the whole structure. We have 10K here, 20K here, 10K here, and we have the shears that we have obtained, 7.5, 15, and 7.5. We have the axial forces here, 6, here 3, here is 9. The moments at the bottom of the column is 60, 120, 60. You can make the checks of summation of y, summation of x, summation of y, and summation of c. You are going to find it like perfect, and you are going to find that all of them are fulfilled, means that it is under equilibrium. I strongly recommend for you to stop the video here and go back, try to go back to this example again and try to solve it by yourself. And whenever that you make any mistake or you are get lost in any point, try to play the video again and check what I have done, and you are going to understand it clearly. Okay, so this is for this portal frame method. I hope that you have understood it well, and there is a home assignment for you. You can go with this, determine the approximate axial force, shears, and moments of all members of the frames shown by using the portal frame method. These are the geometry, and you can solve it based on my procedure and the main hints. Okay, I hope that you have understood really the procedure from this video, and I hope that you can get through any portal frame method easily without a problem. And I wish that you solve this home assignment. Thank you, and see you in the next video.